All right, everybody, let's discuss section 4.1 on inverse functions. And so now we're taking our definition of functions to the next level here, and we want to give it some definitions. You want to be able to use the notation properly here for the inverse functions. We want to talk about the graphs of inverse functions. What do we know about those? How we actually go about finding an inverse function in the first place, and then being able to tell us something about the domain and range of an inverse function. So all of these things are information you should be able to know. So there's this definition on page 334. It says if the ordered pair of a function g are the ordered pairs of a function f with the coordinate points reversed, then g is the inverse function of f. Well, that seems a little bit like a difficult kind of idea to interpret right here. Let's go through an example. Let's say that f of x is the kind of function that is defined by the ordered pair 0, 3, 2, 5, 4, 7, 6, 9, and 8, 11. Well, if f and g are inverses, then by this definition, we should be able to write the function g of x by simply reversing the ordered pairs. So in other words, if g of x is the inverse function of f of x, then instead of 0, 3, we'll have 3, 0. Instead of 2, 5, we'll have the point 5, 2. Instead of having 4, 7, we'll have the point 7, 4. And down the list we go, just reversing the ordered pairs that we were given in the function f of x in order to come up with our sets of ordered pairs. So instead of 8, 11, it should be 11, 8. Okay. Now this should also give us a little bit of information about domain and range right now. We can actually address this a little bit. What is the domain of f? Well, the domain of f is the set of all the x values in our ordered pairs. So for f, the domain was 0, 2, 4, 6, and 8. And the range of function f was the ordered pairs 3, 5, 7. Good Lord, that's a horrible way to write 7. These pens, I don't know, leaky pens. 5, 7, 9, and 11. Right? These were our range values for f of x, right? Domain is the set of all the x values. The range is the set of all the y values. What about g? Well, the domain of g happens to be the set 3, 5, 7, 9, and 11. And consequently, you can see what's going to happen with the range of g. It's going to be the set of all the values, including 0, 2, 4, 6, and 8. They reverse. For an inverse function, all the values that are in the domain of one function are in the range of the inverse. And all the values that are in the range of the original function are the domain of the inverse. So that's going to be really, really helpful to us here shortly. All right, let's talk about this. Do all functions have inverses, right? We've talked about functions that are ordered pairs. What about functions that we can graph? Like, well, let's talk about f of x equals x squared minus 4 that I show below here. Well, if we are able to find an inverse, then every set of ordered pairs that we have on the graph of f of x will be, all our xy points will become yx points. Right? So for example, instead of passing through a point like 0, negative 4, it should pass through the point negative 4, 0. Instead of passing through the point 2, 0, it would pass through the point 0, 2. And on down the line. Instead of negative 2, 0, it would be 0, negative 2. And that presents us with a problem, because if we were to graph out all of those points, what would happen? Well, that would happen. And what's the problem with that? Well, if you looked at that and you said, that does seem a little funny, we would say that, yeah, you're right, because it's not a function, right? In order to be a function in the first place, it has to pass the vertical line test, which this does not. The vertical line test says that if we have the graph of an equation and we pass a vertical line through that equation, it should only pass through the equation in one and only one place. It's true for f of x that it is a function, but it is not a function that has an inverse function. So this problem right here must be resolved. Now, if we look at the function of g of x and ask, well, does this one have an inverse? Most certainly. If we take a look at its graph, and we take a look at the graph of what would be its inverse, we do see that both of those equations have functions that cross the same lines, right? In other words, they do repeat. So we say that in order for us to have a function that has an inverse in the first place, it has to be able to pass what's called the horizontal line test. It has to be one-to-one. The first function right here is not a one-to-one function. Right? So f of x is not one-to-one. If we were to try and draw a horizontal line through it, that horizontal line passes through the graph in more than one point. That is, for each value of x, there's a value of y that goes with another value of x, right? In order to be one-to-one, each value of x must be assigned to exactly one value of y, and each value of y must be assigned to no more than one value of x. Our function to the right over here, yes, this is a one-to-one function, because if we pass a horizontal line through the graph of the function, we only get one and only one value of y corresponding to any given value of x. Right? So we define this as being one-to-one function, so that means that it does have an inverse. So the only time that we have an inverse function is when we have a one-to-one function. All right, more to come in the next few videos.